We're going to spend some time over the next few class periods learning about how calculus can explain rainbows. Yes, calculus can explain rainbows, as well as some physics. Rainbows are created when raindrops scatter sunlight. You might know from experience that you typically see rainbows more in the morning or in the evening when the sun is low in the sky. And of course, is at your back, say, as you look the other direction and there's rain in the air from clouds, you might see a rainbow. They have fascinated mankind since ancient times and have inspired attempts at scientific explanations since the time of Aristotle, which is a couple thousand years ago. In this project, we use the ideas of Descartes and Newton to explain the shape, location, and colors of rainbows. Why do they look like a bow? Why are they in the spot in the sky that they are? And why are the colors separated? Oh, then the copying didn't get so good here. Sorry about this. The figure shown right here shows a ray of sunlight. That's this beam right here. That's the ray of sunlight coming from the left, essentially horizontally. The sun is low in the sky. Entering a spherical raindrop at the point A right there. Are raindrops spherical? I think they're pretty close to spherical, even as they're falling, maybe slightly off. They don't look spherical as you're looking at them, right? Because that's an optical illusion, because you're seeing a streak, because they're moving fast enough that they don't look spherical. Some of the light is reflected, so it hits this drop of water at this point and gets reflected. It bounces off. Here's a line that's tangent to the circle. They're not showing what's getting reflected. What's getting reflected would go off this direction. This angle that you can see here, it's labeled with the Greek letter alpha, is the angle between the light ray and this dashed line, which is perpendicular to the tangent line. It's called a normal line for the circle. That's the angle of incidence right there. Some of the light is reflected, but some is refracted in this direction right here. Refracted essentially means it was bent. There's bending going on. Yes, light bends. Of course, we could get into what is light. Light is both an electromagnetic wave and is also consists of photons. What are they? It's kind of mysterious. It's a quantum mechanics thing. I won't go into detail. We can pretend we've got light rays. It got bent. The angle alpha got converted to a smaller angle beta. And the amount of bending is given by that angle right there. Alpha minus beta is the amount of bending. And in fact, Snell's law, oh, this is hard to see, says sine of alpha equals k times sine of beta. Sine alpha equals k times sine of beta. Is what that says, where again, alpha is the angle of incidence right there. And beta is the angle of refraction right there. Beta, you can see, is a little smaller than alpha. In order for this equation to be true, k would have to be bigger than 1. Because if beta is a little smaller than alpha, sine beta, these are both between 0 and 90 degrees, sine beta will be a little smaller than sine alpha, so k would have to be bigger than 1. In fact, k equals 4/3 is the index of refraction for water. Not exactly 4/3, approximately 4/3. About 1.33333. At this point, B, some light passes through and probably gets refracted as well, though it's not clear from the picture how much. And some light gets reflected. Some light passes through and is refracted into the air, but the line BC shows the part that is reflected, is what that word says, in this direction. That's a reflection. It's bouncing off that part of the water droplet's boundary, the surface. Once again, the angle of incidence equals the angle of reflection, so these betas are actually the same. These two angles are actually the same. When the ray reaches point C, part of it is reflected, that's not drawn, bounces back through the water droplet. We're more interested in the part that is refracted. More interested in the part that leaves the raindrop. It is refracted away from the normal line like this. So we got three turns that go on effectively. There's a refraction here going from here to here of angle alpha minus beta. There is a turning going on from here to here by an angle that's about like this. And that angle right there in degrees would have to be 180 degrees minus whatever this angle is. In radians, that would have to be pi minus 2 beta, because pi radians is 180 degrees, and both of these two angles are beta. And then there's a final small amount of turning going from this direction to this direction, specified by that angle right there, and that's also alpha minus beta. So the total amount of turning, called the angle of deviation, is the sum of those three angles. Alpha minus beta, pi minus 2 beta, and another alpha minus beta. There's two alphas, so you get 2 alpha, and there's a minus beta there, a minus 2 beta there, and a minus 4 beta there. You get a minus 4 beta, and the pi can just go in front. The first thing for us to do is to show that the minimum value of this function of alpha, the minimum deviation is about 138 degrees and occurs when alpha is about 59.4 degrees. So that's going to be the first thing that we are going to do here. D of alpha is pi plus 2 alpha minus 4 beta. This seems to be a function of two variables. This is our objective function. Our objective is, according to the directions, to minimize this. Why? That's not clear. Why do we want to minimize this? It is related to explaining rainbows. But we've got two variables. Do we have to use multivariable calculus? No. There's a constraint. We can get beta in terms of alpha. How? With Snell's law. Snell's law gives us a relationship between alpha and beta. We could solve this equation for beta in terms of alpha. Sine of alpha equals k times sine of beta. I'll put parentheses here now. I want to solve for beta. I guess I should divide both sides by k. And then take the inverse sign? Question?
What does k represent again?
K is the index of refraction. For water, it's about 4/3. I could go ahead and plug 4/3 in here, but we will see it's better to leave it as an unspecified parameter. It's really a family of problems we're trying to solve all at once here. That'll be helpful for thinking about the different colors we will see of the rainbow. So I guess beta is the inverse sine of sine of alpha over k. Really? I guess so. Now, before we rush too quickly into using this, assuming this is right, let's think about it. Inverse sine, when you plug in a number between -1 and 1, it gives you an angle, so to speak, between negative pi over 2 and positive pi over 2. Negative 90 degrees and positive 90 degrees. We do want to think of our angles as positive. Yeah, I mean, if alpha is positive, sine and small 0 to 90 degrees, then sine of that will be positive. K is positive. We're plugging a positive number in here, evidently less than 1, into the inverse sine function. We're going to get an angle out between 0 and pi over 2 radians, 0 and 90 degrees. Is sine of alpha divided by K less than 1? Yeah, because K actually has to be bigger than 1. I mean, for water, it's 4/3. That's bigger than 1. For other liquids, K is also bigger than 1. There is some amount of refraction that goes on no matter what the liquid is. Can this be simplified? If K were 1, it would simplify, wouldn't it? To just alpha? Inverse sine of alpha would be alpha, as long as alpha is between negative pi over 2 and positive pi over 2. But K is bigger than 1, so you can't do anything with this other than leave it like it is. But we can take this and plug it back in there in place of beta. So this all implies that d of alpha is pi plus 2 alpha minus 4 times inverse sine of alpha over K. Ugh. That's an equal sign here. This is the function now I have to minimize. I got to differentiate this with respect to alpha. Yeah, it's not too bad. Maybe before we do so, though, let's see how the graph this looks like. I better not use a capital D in Mathematica. Capital D is reserved for derivative. I'll use a lowercase d. Escape, P escape makes a pi. Plus 2 alpha. A escape makes an alpha. In Mathematica, inverse sine is arcsine, capital A and capital S. Sine alpha over K, and K is a parameter. Maybe I better use a subscript to emphasize that D depends on K, like this. That's okay to do in Mathematica, just like I did by hand in class on Monday. If I want to confirm that it's stored in memory now, I could go D sub K of alpha. There it is. What does the graph of this look like for different values of K? I can make a plot and put it inside something called manipulate, which you had on your project, to make a slider-enabled animation of this as K varies. What should alpha vary over? Alpha is the angle of incidence. You should realize that when the light ray just barely hits the raindrop up here, the normal line is about like this. The angle of incidence is large in that case. In the limit is close to pi over 2. Whereas if the light ray comes in this way, the angle of incidence and the normal line are the same, and the angle's 0. So alpha can vary between 0 and pi over 2. 0 to pi over 2. Maybe fix a plot range here in the vertical direction. They say 0 to, I don't know, maybe pi. But then what's K? Well, for water, K is 4/3. K has to be bigger than 1. Maybe I should go down to 1.1 and as high as, I don't know, 2. Let's just try it and see what happens. So when I enter this, it's going to be the graph of the function I'm interested in when K is 4/3. There it is, and we see it does look like it has a minimum. Where is that minimum? The horizontal axis here is the alpha axis. The minimum is close to K is, or alpha is a little bit bigger than 1. 1.075 radians. Alpha is an angle in radians. In degrees, that is close to 60 degrees, actually. 60 degrees is pi over 3 radians, just a little bit bigger than 1. And guess what? That number is close to 60 degrees. It looks like it's going to work. Now, the Mathematica does allow me to change this graph for different values of k. As k changes, I get different graphs representing deviation angles for different liquids, I guess. Water versus something else, or possibly for different colors of light even. Maybe the color affects the angle of refraction, and it does. The wavelength affects the angle of refraction. Let's finish today with this project by differentiating, setting it equal to 0, and seeing if we can solve for the critical point. I'll try to do that relatively fast. The d prime of alpha is 2 minus, oh boy. Derivative of inverse sine is 1 over 1 minus x squared. I got a 4, that's got to stay there. But in place of x, I need to replace it with sine of alpha over k. So I get sine squared alpha over k squared. Then the chain rule gives me an extra factor of cos alpha over k, the derivative of sine alpha over k with respect to alpha. Set this equal to 0 and solve for alpha. Yikes. Well, let's see. I can bring the thing that I'm subtracting over to the other side. I can also write k as square root of k squared. And that is okay to do as long as k is positive, which it is. K is positive. So k can be thought of as the square root of k squared. Square root of k squared in general is the absolute value of k. But if k is positive, that's fine. And then you can combine these square roots into one square root and multiply the k squared both times 1 and times this to cancel the k squared in the bottom. That's nice. Now I don't have any more fractions within fractions. A little bit more cancellation. The 2 and the 4 can cancel, effectively dividing both sides by 2. And ultimately, what it looks like is I want the equation 2, this fraction to equal 1 ultimately. So 2 cosine of alpha should equal the square root. I'm trying to solve for alpha, Get rid of the square root next, square both sides. How do I solve this for alpha? Think trig identity. Maybe I should replace sine squared with 1 minus cos squared, right? That's a trig identity. I also could have replaced cos squared with 1 minus sine squared. Again, remember what you're trying to do. Solve for alpha. Maybe I should subtract cos squared from both sides and get this. And then divide both sides by 3. Then take the square root. Cos alpha is the square root of k squared minus 1 over 3. So it looks like alpha is the inverse cosine of the square root of k squared minus 1 over 3. Really? That's our critical point? Yep, I checked this ahead of time. This is right. Does it match the book's answer or the project's answer when k is 4/3? 4/3, square it, subtract 1, divide by 3, take a square root, then take the inverse cosine. 1.04 radians, how many degrees? Multiply by 180 over pi. 59.4 degrees. We got the right answer. That's the angle at which the maximum deviation or the minimum deviation occurs. That's the angle, about 59.4 degrees, at which the minimum value of the deviation, being 138 degrees, occurs. The output of D of alpha for this input is about 138 degrees. Redrawing the graph over here. If we think of the angles as being in degrees, that's not what we were doing, but if we did, this is about 59.4 degrees, and the angle, the deviation angle, is about 138 degrees. How is this related to rainbows? What in the world? Here's the key. We'll talk more about this on Friday. What's the significance of this? This is where the derivative d prime is 0. This means, here's the key sentence, this means many rays whose angles are very close to 59.4 degrees become deviated by approximately the same amount. Huh? Because the slope is 0 at the minimum here, there are many angles relatively close to 59.4 degrees that when you plug them into D to find the deviation angle, you get an output close to 138 degrees, very close, because the graph's so flat there. The tangent is horizontal. That means for many light rays coming in here, how many light rays? Well, infinitely many. For a certain band of light rays coming in at an angle alpha close to 59.4 degrees, they all end up getting deviated by about the same amount, meaning effectively they come out of the raindrop at about the same spot. And so you see them concentrated in the sky. That's the way your eye perceives them. That's not explaining the colors yet. What we're going to see on Friday with the colors is the K is slightly different for different colors.